The universe has cracks in it, literal scars stretching from one end of existence to the other, and we have absolutely no idea if they're there. Today, we're going to find out what they are, why scientists think they might exist, and how we're hunting for them right now. I'm FactSpark. If this is your kind of thing, hit subscribe. We go deep on stuff like this every week. So, cracks in space. Let's start with something you already understand. Picture a frozen lake in the middle of winter. The surface doesn't freeze all at once. It starts in multiple spots simultaneously. Tiny ice crystals forming in different places, growing outward. And here's the thing. Each of those crystals has its own orientation, its own internal structure. When two of them meet and try to merge, they don't fit perfectly. They crash into each other and leave a scar at the border, a crack through the ice. Now, and stay with me here, the universe did something almost identical. It started unimaginably hot, denser than anything we can picture. And ever since the Big Bang, it's been expanding and cooling. And as it cooled, it went through a series of phase transitions, moments where the fundamental nature of reality shifted, just like water turning into ice. One of the most dramatic examples happened in the first microseconds of existence. Back then, the universe was so hot that the basic building blocks of matter, quarks and gluons, roamed completely free, forming a kind of particle soup. Then, as the temperature dropped, they snapped together to form protons and neutrons. Same basic idea as water molecules locking into a crystal lattice.
But here's where it gets really interesting, and this is the core question we need to answer. When matter freezes like this, does the universe leave scars? To understand that, we need to talk about symmetry. In liquid water, every direction looks identical. There's no preferred axis, no special orientation, it's completely uniform. But the moment it freezes, that changes. The molecules arrange into a rigid grid, and suddenly, direction matters. Scientists call this symmetry breaking, when something that was equal in all directions suddenly isn't anymore. The same thing happened during certain phase transitions in the early universe. Things that used to look identical stopped looking identical. And just like with ice, that breaking of symmetry could produce defects. So how exactly does a universe break its own symmetry? To explain that, we have to think about something called fields. Modern physics tells us that everything in the universe, every particle, is actually a ripple in an invisible field that stretches across all of space. There's an electron field, a quark field, and so on. Think of it like the surface of an ocean. Particles are the waves on top of it. Now, there's a special class of fields, scalar fields, that are responsible for breaking symmetry. The most famous one is the field associated with the Higgs boson, and we can visualize how they work like this. Imagine a ball sitting at the top of a hill. It has a lot of potential energy and desperately wants to roll down. When the universe is hot enough, that hill is shaped like a simple bowl, and the ball sits in the center, stable. But as the universe cools, the landscape changes. The hill transforms into something that looks like a sombrero, a ring-shaped valley surrounding a central peak. The ball is now sitting at an unstable high point. It has to fall into the ring. But which direction? There's no preference. Every direction looks the same. And here's the critical part. In different regions of the early universe, separated by huge distances, that ball starts to fall in different directions simultaneously. In one region, it falls left. In another, far enough away that they can't influence each other, it falls right. These regions grow and spread outward until they collide. When they meet, you have a problem. At the boundary, the field goes from one side of the valley to the other, but to get there, it has to pass over the central peak. That means at the boundary, the field is stuck, trapped in a high-energy configuration it can't escape. A defect has formed. Now, depending on the shape of the potential, the landscape the field rolls through, you can get different types of defects. If the landscape has two distinct valleys, the defect is a flat surface, a two-dimensional wall called a domain wall, separating regions of the universe like a membrane through space. If the valley forms a complete ring, like that sombrero,
then the defect that forms is a line, a one-dimensional structure threading through space. That's a cosmic string. And if the geometry is even more complex, you can get point defects, isolated spots called monopoles. Now, here's something worth pointing out before we move on, because I know some of you are already thinking it. Cosmic strings have almost the same name as the strings from string theory, and I want to be clear, these are completely different things. Cosmic strings are enormous, macroscopic defects in the structure of space.
String theory strings are the hypothetical fundamental objects thought to make up particles at the tiniest possible scale. Same word, completely different concepts. We'll come back to why that's actually interesting in a moment. Let me ask you something, and I genuinely want to know your answer in the comments. If you had to bet, do you think cosmic strings are out there right now, threading through the universe? Yes or no? Write it down. We're coming back to this. So, which of these defects is the most interesting to physicists? Domain walls, it turns out, would be catastrophic. If they'd formed in the early universe, they would have stored so much energy that they'd have completely taken over the expansion of space. The universe would look nothing like what we see. Same story with monopoles. They'd have been so abundant that we'd be drowning in them. Cosmic strings, though, are different. They're extreme objects, but they're survivable. And the reason has to do with how they behave. A typical cosmic string would be longer than the entire observable universe, stretching from one edge of what we can see to the other. And despite being unimaginably thin, possibly thinner than a single proton, they pack a staggering amount of energy into every meter of their length. 1 kilometer of cosmic string could outweigh the moon. But here's the counterintuitive twist. If you floated in space right next to a cosmic string, you wouldn't feel any gravitational pull toward it. The two effects balance out exactly. From up close, you'd feel nothing pulling you in. What you would notice, though, is that something is off about the space around it. This is where cosmic strings get truly strange. If you traveled in a complete circle around a cosmic string, you wouldn't complete 360 degrees. You'd complete slightly less. A small slice of angle is simply missing from the geometry of space around the string. Scientists call this an angular deficit. Think about a flat circle of paper. Draw 2 parallel lines across it. Now cut out a thin triangular wedge and tape the edges together. The paper curls into a cone, and those parallel lines you drew, they're no longer parallel. They converge. That's what a cosmic string does to space. 2 objects traveling on either side of a cosmic string, even without feeling any direct gravitational attraction, would be nudged toward each other. Light behaves the same way. If a cosmic string passed between us and a distant galaxy, light traveling on either side of it would be bent inward. Our telescope would pick up 2 images of the same galaxy, perfectly identical, with no distortion, separated by a tiny angle that matches the angular deficit exactly. This is similar to gravitational lensing, where massive objects bend light from background sources. But there's a key difference. Normal gravitational lenses produce distorted, stretched images, arcs, rings, smeared blobs. A cosmic string would produce 2 crisp, identical copies, a clean double image with no stretching. And at the start of this century, astronomers thought they'd found exactly that. 2 galaxies appeared unusually close together in the sky. They looked almost identical. Same shape, same brightness, same colors. The possibility was seriously entertained. Maybe this was one galaxy, seen twice, with a cosmic string threading between us and it. The scientific community got genuinely excited. Then the Hubble Space Telescope got a closer look. They were 2 separate galaxies, just really, really similar. A cosmic coincidence, not a cosmic string. Disappointment doesn't quite cover it. Other candidate double images have been found since then, and every single one has eventually been ruled out. But lensing isn't the only way to search. A moving cosmic string would leave a different kind of signature in the oldest light in the universe, the cosmic microwave background, the faint glow left over from when the universe first became transparent, about 380,000 years after the Big Bang.
As a cosmic string sweeps through space, it compresses the photons ahead of it and stretches the ones behind. The result would be a sharp temperature edge across the sky. One side of the string's path slightly bluer than expected, the other side slightly redder. Astronomers have mapped the cosmic microwave background in extraordinary detail. No such edge has ever appeared. Strike two. But there's still a third method, and this one might actually be working. Cosmic strings move, they vibrate, they whip through space at extraordinary speeds. When two strings cross paths, they can intercommute, meaning they swap partners and reconnect, occasionally pinching off closed loops of string that detach from the main network. Those loops don't sit still. They oscillate, change shape, fragment into smaller loops. And all of that motion radiates energy in the form of gravitational waves, ripples in the fabric of space-time itself.
A network of cosmic strings across the universe would generate a constant background hum of gravitational waves, not from a single event, like a pair of merging black holes, but from countless strings everywhere, all at once, a gravitational wave background filling the entire universe. And here's the thing. In 2023, the Nanograv collaboration announced the detection of exactly that, a gravitational wave background. Now, does that mean we found cosmic strings? Not necessarily. The leading explanation is still that it's produced by pairs of supermassive black holes spiraling toward each other at the centers of galaxies across the universe. That's the boring, expected answer. But some researchers think cosmic strings could be contributing to that signal, and we don't yet have enough precision to rule it out. Future observatories are being built specifically to resolve this. LISA, the space-based gravitational wave detector, the Einstein telescope on the ground, the Square Kilometer Array, which will conduct pulsar timing observations far more precise than nanogravs. These instruments may finally give us the answer. Remember earlier when we said cosmic strings and string theory strings were completely different things? Here's where it gets weird. String theory proposes that the fundamental ingredients of reality aren't point particles, but tiny vibrating strings. At the scale string theory operates on, these strings are unimaginably small, nothing like the cosmic scale defects we've been discussing. But at the start of this century, theorists started finding unexpected mathematical bridges between the two, and the connection runs through the very thing that seemed to kill cosmic strings in the first place: inflation. Inflation is the theory that the universe underwent a brief, explosive period of expansion immediately after the Big Bang, expanding by an incomprehensible factor in a tiny fraction of a second. It explains why the universe looks so uniform on large scales, and it provides a mechanism for how the structures we see today, galaxies, clusters, superclusters, could have seeded from quantum fluctuations. Inflation also, it turns out, could have taken fundamental string theory strings and stretched them, expanded them from the microscopic to the cosmological, blown them up from objects far too small to ever observe into structures that span the universe. These are called cosmic superstrings, and they would behave on large scales almost exactly like the topological defects we've been talking about, except they'd be telling us something even more profound. Not just that phase transitions happened in the early universe, but that the fundamental fabric of reality is made of strings. The two ideas, for decades completely separate, turned out to be pointing at the same thing. So where does this leave us? No confirmed detection. Not through lensing, not through the microwave background, not through gravitational waves. But we haven't ruled them out either. What non-detection does tell us is something about the possible tension of cosmic strings, their energy per unit length, which controls how strongly they interact gravitationally. The more sensitive our instruments get without finding a signal, the tighter the constraints on that tension. Cosmic strings, if they exist, can't be too massive. But there are escape routes. If string loops lose energy not just through gravitational waves, but also by emitting particles, they'd radiate away less gravitational energy, meaning the gravitational wave signal would be weaker and our constraints would loosen. There's still a lot of parameter space where cosmic strings could be hiding. And keep in mind, every time we've built a more sensitive detector, the universe has surprised us. We discovered gravitational waves at all,
something that seemed almost philosophical for decades. We found the Higgs boson. We imaged a black hole. The universe has a habit of revealing things that seemed completely out of reach. Cosmic strings might be next. Go back to the comments now. Did you write yes or no? Because here's the thing. You don't actually need to believe in grand unified theories or string theory to think these objects are worth looking for. The physics that predicts them, phase transitions, symmetry breaking, topological defects, is the same physics we test in particle accelerators. We've seen similar phenomena in laboratory materials. Defects form in liquid crystals. They form in superfluids. We can create cosmic string analogs in a lab. The question isn't really whether phase transitions happened in the early universe. Almost certainly they did. The question is whether any of those transitions left behind topological scars that still thread through the universe today. And the answer is out there, written in gravitational waves, or in the precise temperatures of ancient light, or in the alignment of distant galaxies. We just haven't learned to read it yet. The universe has been keeping this secret for almost 14 billion years. We're getting close.
If you want more of this, subscribe to FactSpark and let me know in the comments, yes or no. Do you think they're real? The discussion down there is always worth reading.